How are you all doing this morning?
Doing well, thank you. How you doing?
Doing great. So, any questions regarding the exam or anything? Because I think that's due tomorrow. Does that sound
Yes,
about right?
yes, sir. It's due tomorrow. Really, I
Uh,
think I'm good on that, but just problem three is the only thing that's kind of bugging me, just because I have no idea if I'm doing it right. But I can't
so,
really be helped there.
I mean, I think, or at least I thought I made it clear. You're looking for. So let me pull up what the problem statement says, and then we'll talk about it. Let's see. I gotta find it. All right, so it says that you are to design a digital to analog converter. So a multi-stage op amp capable of converting a 4-bit binary number into its equivalent base 10 integer as a voltage output. So do you guys know really kind of anything about how binary numbers work?
A little bit.
All right, let me figure out how to do a whiteboard thing real quick. All right, so how really all numbers work um, using the Arabic numerical system. So for instance, let's talk about a base 10 number real quick. So let's say that I have the number 524. This could be expressed as 5 times 10 to the 2 plus, that is not eraser, hold on. 2 times 10 to the 1 plus 4 times 10 to the 0. Are we okay with that breaking it down?
Yes, sir.
So there's 5 in the hundreds digit, 2 in the tens digit, and 4 in the ones digit. So for a 4-bit binary number, let's say that we have 1001. This means that we have 1 times 2 to the 3 plus 0 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. So in a 10-bit digit, that would be, let's see, 8 plus 1 is 9 for a base 10 number, okay? So each of these guys is a register where these ones and zeros are a voltage source that can give either 1 volt or 0 volt. So really what you are trying to design, we can base off of this mathematical operation right here, okay? So we want one input, let's call this voltage 1. I don't know why I did a superscript as opposed to a subscript. Give me a second. To be scaled by a factor of 8. Voltage 2 to be scaled by a factor of 0, voltage 3 to be scaled by a factor, or excuse me, voltage 2 to be scaled by a factor of 4, voltage 3 to be scaled by a factor of 2, and voltage 4 to be scaled by a factor of 1. I think I used different subscripts for these voltages in the problem statement, but it's just 4 different input voltages, and they're each scaled by a different amount. Notice that they're also added together. So what type of operational amplifier circuit could be used to add different voltage signals together and also scale different portions of the voltage signal to different levels?
The weighted summing amplifier.
Exactly right. So the problem with the weighted summing amplifier is that the one that you're likely trying to use inverts the signal, meaning that you would be able to put in positive 1 volts for everything and get out a negative 15 volt output. So you will need a second stage that will uninvert your output from your first stage. I can't go into any more detail than that, than literally just drawing the circuit for you.
Understood, thank you.
Yeah, so I mean, that's should be pretty straightforward, right?
Yes, sir.
All right.
Just on that though, I did design a circuit like that. The only problem was I was getting like 1 or 2 1/1000ths of a volt off of the answer. Like whenever you add a certain voltage together, you get different numbers. Whatever.
What
Is that
size resistors were you using?
less than 1,000?
Okay, so I would keep every resistor above a 1 kilo ohm resistor.
Okay, awesome. Thank you, sir.
Yeah, because the smaller the resistors you use, you're going to introduce a little bit more variation there. So let's see. So I would put your feedback resistor, if I were designing this, as let's see, probably an 8 kilo ohm resistor or a 16 kilo ohm resistor, and then use math to figure out what all the other resistor values in my input stage need to be.
All right, we'll do that. Thank you.
Yep. Any other questions regarding the exam or anything? All right, well, today's lecture material is really pretty much a review on how to convert time domain signals to phasors or frequency domain signals, and developing the relationships that will allow you to do frequency domain circuit analysis. So I guess my question is, do I need to spend time doing any of that, or is the lecture material and your knowledge from Circuits 1 sufficient to go at the homework assignment?
If you don't mind, could you just do like 1 or 2 examples maybe?
Sure. On which specific thing, or just kind of in general?
Just converting between time and phasor domains, probably.
All right, give me just a second. Let me open up. Share screen. There we go. All right, so let's say that we have a time domain signal. I think we'll write VA of t is 17 cosine 33t plus 11 degrees volts. The time domain, or excuse me, the frequency domain representation of this would be a phasor, VA, where I'm putting the bar over the top to denote that it is going to be a complex number. And so I'm going to take my magnitude, which in this case is 17, and take my phase angle, which in this case is 11 degrees, and there's my phasor. So I only include the magnitude and the phase angle. The frequency term is suppressed. Phasors in this class will be entirely constructed using the cosine representation of our waveforms. So if I had a signal VB of t that was 8 sine 3 pi plus 40 degrees volts, I would need to first convert this sine function into a cosine function. Do either of you recall whether I add 90 degrees or subtract 90 degrees to do that?
I think you can do either, but I don't remember.
So you definitely can't do either. So one of them would be effectively converting it to a cosine, but also multiplying it by a factor of -1, and the other one converts to a cosine directly. I believe that it's subtracting 90 degrees, but I don't want to completely screw this up, so give me just a second to give it a Google. All right. So we subtract 90 degrees to go from sine to cosine. All right, so that would be 8 cosine 3 pi minus 3, sorry, this should be 3 pi t minus 50 degrees volts, which gives us VB is the magnitude 8 with an angle of minus 50 degrees volts. So your steps are to convert it to, let's do, I guess, one last example. VC of t, let's call this -4 cosine 8t plus 7 sine 8t. So we also need to be working with a positive magnitude. So this would be the same as 4 cosine 8t plus or minus 180 degrees. Doesn't matter here, so I'm just going to do plus 7 cosine 8t minus 90 degrees volts. So VC would be 4 angle 180 degrees plus 7 angle minus 90 degrees. And now I need to find the calculator real quick because I can't do that in my head. So 4 angle 180 plus 7 angle minus 90. -0.062 angle -11 point, oh sorry, -119. 0.74 degrees volts. So we're always working under the assumption that we're going to have positive magnitudes and cosine functions. So you need to convert your signal to have a positive magnitude by effectively multiplying by a phasor 1 angle 180 or 1 angle -180. And you also need to make sure to convert all of your sines to cosines by simply subtracting 90 degrees from the phase angle. So that's converting from the time domain to the frequency domain. Excuse me. So is that
Quick
all?
question.
Yes.
The frequency will, if that's different, we cannot combine them, right?
Yes, if the frequency is different. So if we had these two signals have different frequencies, so they cannot be combined. Now in circuits 2, we are going to learn how to approach problems that are excited with multiple frequencies. And the end result of that is just going to be that we have to apply the superposition technique. The reason being is that, do you remember anything about impedances?
The equivalent impedance and all that.
Yeah, so like the impedance of a resistor is the resistor value itself. The impedance of an inductor is j omega times L, so it's the imaginary operator times the excuse me, angular frequency times the inductance value. And the impedance of a capacitor is 1 over j omega c, which we could also express as negative j divided by omega c. I don't know which teacher you had, so you might have seen it either of those ways. So the impedance of an inductor depends on omega, and the impedance of a capacitor depends on omega. For a voltage signal like this, there are two different omegas, and so the only way to analyze that circuit would be to use the superposition principle and look at it one frequency at a time, which is a perfectly valid way to analyze circuit. So let's see, I think either Thursday's lecture or next Monday's lecture is about that very thing, analyzing multi-frequency circuits. Yeah, I think it's Thursday. But anyway, so for the time being, you definitely can't convert this into a single phasor.
All right, thank you.
Okay, so unless there's any other questions, I guess we're kind of wrapped up for the day. Again, it's largely review. On my YouTube channel, so not only do I have some notes about converting from the frequency domain to the, time domain to the frequency domain and vice versa, developing phasor relationships for resistors, capacitors, and inductors, and from that deriving equations for impedance, which we've done here, as well as admittance, which is just 1 over the impedance. On my YouTube channel, there's also lectures on a review of complex numbers and a review of sinusoids, which may be useful to you guys since we're going to be dealing with a lot of complex numbers and sinusoids over the next couple of days. So definitely wouldn't hurt you to review that if you're feeling unsure of your skills in this steady state sinusoidal circuit analysis that we're going to be doing. All right, so unless either of you guys have anything else, we'll wrap up for the day.
I'm good to go.
All righty, well, I'll see you gentlemen tomorrow morning. Hopefully you get your tests and all that kind of jazz finished up, and yeah, catch you later.
All right, have a good one. Thank you.